In the previous video, we spoke about a mass moving under the influence of a spring. So now let's see how we can draw it on this paper here. And let's think of a floor and a wall, and the spring is attached to the wall. Remember, this is a massless spring, and we have our little mass here. And let's say it's moving on wheels, so there is no friction. And what we do is, if this is the beginning length of the spring when nothing is moving, the spring is at its rest length, then we move it a little bit to this side. Now the mass is here. And this distance, we call it delta x. We just moved it. And it's going to start to oscillate back and forth. And it will go back to this point and will move also the same length to this direction, delta x, also to this direction. So it will oscillate back and forth. And this is a nice technical way to draw it. And the mathematical description would look like this. So we're beginning with Newton's second law, F equals ma. And do you remember what A means mathematically? A is actually the second derivative according to time of the position x. We have another way of writing this down. We write m x dot dot. That's a shorthand for second derivative according to time. One dot would be the first derivative according to time. And as we saw in the previous video, f is proportional to k times x. So this is if we assume that the initial position was at x equals 0. So if we write it down in a nice short way, we see that kx is equal to mx dot dot. So in other words, the second derivative according to time of x is equal to some kind of constant times x itself. And from here, this is an ordinary differential equation, and we can get a sine function or a cosine function according to our choice. Okay, so this is a classic harmonic oscillator.